In 1915, a wooden ship sank to the bottom of the Antarctic Ocean. Nobody knew where it was, nobody could reach it, and for 107 years, the ocean kept it. Then, in 2022, a team of explorers sent cameras 3,000 meters down into one of the most hostile places on the planet, and what they found stopped everyone cold. The ship was still there, not as a ruin, not as wreckage scattered across the seafloor, but as a ship. The name on the stern was still legible. The masts were still standing. The wood looked as if someone had simply walked off the deck and never come back. Now hold that image for a moment, because somewhere else in the same ocean, the RMS Titanic, made of steel, far more massive, is actively dissolving. It is being eaten alive by bacteria. Its railings are collapsing. Its grand staircase is gone. Scientists estimate it could be unrecognizable within the next 2 decades. 2 ships, both on the ocean floor, and they could not be more different. This is not a coincidence. This is a story about what happens when the ocean's rules stop working, and what that reveals about time, decay, and the strange physics of survival at the bottom of the world. To understand why Endurance survived, you first have to understand how it was lost, because the way a ship sinks matters more than most people realize. In 1914, Ernest Shackleton launched what he called the last great journey left to make on Earth, a crossing of the Antarctic continent from sea to sea. His ship, the Endurance, was purpose-built for polar conditions. 3 layers of wood, reinforced bow, a hull designed to deflect ice rather than resist it. But the Weddell Sea had other plans. The ship became locked in pack ice before it ever reached the continent. And for the next 10 months, Shackleton and his crew of 27 men watched helplessly as the ice moved. Not violently, not with the drama of crashing waves. The ice pressed slowly, relentlessly, from every direction at once, a force so gradual it was almost invisible until it wasn't. The ship groaned for weeks before it finally gave way, and when it sank, in November 1915, it sank mostly intact. It did not explode. It was not torn to pieces. It descended through nearly 3,000 meters of freezing water and came to rest upright on the seafloor as a structure, not as debris. Shackleton and every member of his crew survived, but the ship was gone, and it would remain gone, and unfound, and utterly untouched for the next 107 years. Here is what the ocean normally does to things that fall into it. It processes them. Every wreck that sinks becomes a site of controlled destruction, dismantled by a system that has been running for billions of years. Temperature accelerates chemistry. Oxygen fuels corrosion. Microbes colonize every available surface, consuming iron, wood, rubber, glass, anything with stored energy. Currents carry nutrients in and carry particles out, and slowly, methodically, the ship stops being a ship and starts being an ecosystem. Then it stops being an ecosystem and starts being sediment. This is exactly what is happening to the Titanic right now, in the North Atlantic. A species of bacteria called Halomonas titanicae has colonized the iron, metabolizing it into fragile rust formations, structures called rusticles that are visually dramatic but structurally worthless. They collapse under their own weight. Entire sections of the bow have already disappeared. The Titanic is not decaying. It is being actively consumed by a living system that finds it nutritious. And the terrifying thing is that this is normal. This is what the ocean is supposed to do. When the ocean does not do this, when a ship survives on the seafloor for a century and looks the way Endurance looks, something has gone wrong with the system. Or rather, something has gone right, in a way that almost never happens. The first thing that has gone right in the Weddell Sea is temperature, and not just in the obvious way. The water surrounding Endurance sits at approximately -1.8 degrees Celsius. That is not simply cold. That is the physical edge of liquid seawater. Below that temperature, salt water begins to freeze. At that threshold, the behavior of molecules changes in ways that cascade through every chemical process in the environment. Molecular motion slows. Reaction rates drop not linearly, but exponentially. A corrosion process that would take 1 year in temperate Atlantic water might take 20 years here. An organic breakdown reaction that would complete in a decade in the Pacific might require 2 centuries in the Weddell Sea. Even the diffusion of oxygen, the process by which oxygen moves through water to reach surfaces and drive oxidation, becomes sluggish and inefficient. This is not an environment that is merely unfriendly to decay. It is an environment where the chemistry of decay has been throttled at the molecular level. Every reaction that wants to happen is happening at a fraction of the speed it would anywhere else on the planet. The ocean is cold everywhere at depth. But this cold is different. This is cold at the edge of what liquid water can be, and that distinction matters enormously. But temperature alone has never been enough to explain what happened to endurance. There are cold places in the ocean where life still thrives, where microbial ecosystems have adapted to the dark and the pressure and the chill, where hydrothermal vents create islands of biological activity, where even in the deepest trenches, organisms have found a way to consume whatever falls. Cold slows the system. It does not stop it. What makes the waters surrounding endurance different is not just their temperature. It is their isolation specifically, their isolation from energy. The Weddell Sea participates in one of the great circulation systems of the global ocean. Dense, cold, oxygen-rich water forms at the surface near Antarctica and sinks, traveling along the seafloor in currents that eventually reach the rest of the world's oceans. This process brings oxygen down, but it brings almost nothing else. No warm nutrients from sunlight-driven surface productivity, no organic material from shallower ecosystems, almost no energy inputs that microbial life could use to build and sustain itself. The seafloor around endurance is biologically impoverished in a way that goes beyond temperature. It is a system that has been starved of the inputs that life requires. And without life, the biological pathways of decay, the ones that are dismantling the Titanic right now, simply cannot operate at meaningful scale. And then there is the absence that matters more than almost anything else. In most oceans, wooden ships do not simply rot. They are eaten from the inside out by organisms called shipworms. Despite the name, shipworms are not worms at all. They are a family of saltwater clams, elongated and specialized, that use a pair of small shells like drill bits to bore into submerged wood. Once inside, they consume it. They digest the cellulose. They grow within the tunnels they create. And they reproduce, spreading through a wooden structure until what looked like solid timber is actually a labyrinth of hollow channels, structurally compromised, held together by almost nothing. Entire ancient fleets have been lost to shipworms. Maritime archaeologists often find almost no trace of wooden ships from past centuries, not because they disintegrated, but because shipworms left nothing worth finding. The animals are that effective, but shipworms have a biological constraint that they cannot overcome. They require water temperatures well above freezing to survive and reproduce. In Antarctic waters, they cannot live. And so the single most destructive force in the history of wooden shipbuilding is simply absent from the environment where endurance rests. The ship is not fighting off an attack. There is no attack. The predator that has erased more maritime history than any other force on Earth cannot exist here. The seafloor itself adds another layer of protection that is easy to overlook. In most regions of the ocean, the bottom is not still. Currents move. Sediment drifts. Particles suspended in the water column act as a slow, continuous abrasive, wearing down surfaces over time. And those same currents transport organic material fragments of dead organisms, drifting from the surface that feed microbial communities on the seafloor. Energy in, life grows. Life grows, decay accelerates. It is a cycle, and it runs continuously in most of the world's oceans. In the Weddell Sea, that cycle is severely muted. Currents near the seafloor are weak. Sediment transport is minimal. What oceanographers call marine snow, the slow rain of organic particles descending from the surface, falls here too, but in an environment so cold and so energy limited, it barely registers as a food source. The wreck of Endurance is not being buried, it sits exposed on the seafloor, visible in every direction. But it is also not being ground down by moving water, and it is not surrounded by thriving communities of organisms finding nutrition in the organic material that a more active current system would deliver. It exists in a condition that has no real equivalent anywhere else in the ocean. Exposed but uneroded, present but invisible to the biological systems that would normally have claimed it long ago. There is one more factor that most people never consider, and it is one of the most counterintuitive. At 3,000 meters of depth, the pressure bearing down on Endurance is roughly 300 times the atmospheric pressure at sea level. That is the kind of number that makes implosion feel inevitable. But pressure, in this case, is not destroying the ship. It has become part of what is protecting it. When Endurance sank, the air spaces inside the cargo holds, the crew quarters, the sealed compartments collapsed under the increasing pressure as the ship descended. By the time it reached the seafloor, those internal spaces had equilibrated with the external environment. Internal pressure and external pressure became equal. And at that point, the destructive potential of pressure essentially disappeared. There were no longer any pressure differentials working to deform or collapse the structure. What remained was immense but constant. And constant pressure does not destroy things the way fluctuating pressure does. Compare this to a shallow water wreck. Sitting in 10 or 20 meters of water, subjected to wave action, cyclic compression and decompression, surge and retreat, repeated thousands of times a day, every day for years. That motion fatigues materials, it opens joints, it works water into cracks and lets it expand. None of that is happening to Endurance. The deep ocean, for all its pressure, is the most mechanically stable environment on Earth. And stability, it turns out, is one of the most powerful forms of preservation that exists. This is the point where the individual factors stop being a list and become something more than the sum of their parts. Near freezing temperature, energy starvation, absence of shipworms, minimal currents, physical stability. Take any one of these conditions alone and it would slow decay. Take any two together and it would slow it significantly. But in the Weddell Sea, all five operate simultaneously and they reinforce each other in ways that compound their individual effects. Low temperature slows chemistry and suppresses microbial growth. Suppressed microbial growth means less oxygen consumption, which means more oxygen stays dissolved but less reactive. Minimal currents mean less organic input, which further starves what little biology is trying to establish itself. No shipworms means the primary vector for internal wood destruction is simply gone. And physical stability means no mechanical stress is accumulating in the structure over time. Every pathway of decay is constrained. Not one of them is dominant. Not one of them has found a foothold and begun to accelerate. This is the combination that does not exist anywhere else in the ocean with this consistency. It is why Endurance sits on the seafloor looking the way it does. It is why researchers who spent careers studying deep-sea wrecks were still visibly shaken when the footage came back. The ocean has rules. In the Weddell Sea, those rules have been suspended. Ernest Shackleton never knew his ship was intact. He died in 1922, 3 years before the footage that would have shown him the name still painted on the stern, the wheel still mounted in place, the hull still whole. He survived the loss of the ship. He led 27 men across open ocean in a lifeboat to reach help, and every single one of them lived. The expedition that failed to cross Antarctica became, instead, one of the greatest survival stories in human history. But the ship that carried them to the edge of that story, the one they watched sink, the one they grieved for, the one they assumed the ocean had dissolved into nothing, was waiting. Beneath 3,000 meters of frozen water, in the most inaccessible place on Earth, The Endurance had been sitting untouched for a century, preserved by a combination of conditions so specific and so rare that they may not exist anywhere else on the seafloor. And what this tells us goes beyond one ship. It tells us that the ocean does not erase history the way we assume it does. It tells us that decay is not a universal constant. It is a product of specific systems. Change the system, and you change the outcome. There are moments from the human past that we believe are gone forever, dissolved and processed and lost. Some of them may not be. Some of them may be waiting, in cold and silent places we have not yet learned to reach, held in suspension by the same quiet physics that held Endurance intact, legible, unchanged for longer than anyone thought possible. If you're drawn to places where the rules of the ocean begin to break down, where physics, biology, and time intersect in ways that science is still trying to explain, follow Sunken Realms Deep. Because far below the surface, the ocean is not just a place where things are lost. Sometimes, it is exactly where they are kept.